cutting tool materials. So we have seen various types of cutting tool materials and their properties. So, and how do you select those cutting tool materials for different cases? Like, okay, if you want to operate at low speeds, what is the cutting tool? If you want to increase the speed, what is the cutting tool? Okay. So for finish machining, for rough machining, what are the cutting tools used? Those things we have seen. We have seen the properties of all the cutting tools, and okay, we have understood when to use which type of cutting tool. So with that, we completed our discussion on cutting tools. Now let us have a look at the thermal aspects of machining process. So during machining, temperature will be generated, heat will be generated, and of course you can sense the heat in the form of temperature. Now what is the source of heat generation during cutting process? How this heat is getting generated? Now what is the impact of that heat generated on the tool and the workpiece and the chip? And how do you control the temperature? Or first of all, how do you measure the cutting temperature? And how do you reduce the heat generation or the temperature that is being produced? So we are going to discuss those aspects now. So let me present. Thermal aspects. So thermal aspect is nothing but temperature. Heat is being generated, so temperature will raise. So, so approximately 98% of the energy, okay, in machining is converted into heat. So that means you are cutting the workpiece and you are using certain amount of power for cutting process. Okay, we have calculated that also. Cutting power, cutting force into cutting velocity is the cutting power. So 98% of that cutting power that you are providing is converted to heat. Now this heat is generated due to plastic deformation of the material. So material in front of the tool tip is subjected to compression. Okay, that compressive force will make that material like a plastic. Okay, the material will go to plastic state. So then high amount of temperature will be generated. So remaining energy is retained as elastic energy in the chip. So very minor quantity of energy will be stored as elastic energy in the chip. So chip will be removed and that chip will have this spring back effect. Once it is cut, okay, it is being bent, and once it passes the tool, it will try to call back. Okay, it will try to come to its original state, but it will not come completely. Okay, some portion. So that is elastic energy. So these temperatures are very high at a tool chip interaction. Okay, there are 3 zones actually during cutting process. We'll see them. So among these 3 zones, chip tool interaction That means the chip is rubbing against the rake face of the cutting tool. So at that location of rubbing or the interaction between the chip and tool will have the high temperature. Now, hot chips that pose safety hazards to the machine operator. So as the result of the heat that is generated, chips will be very hot and they are difficult to handle for the operator. So that is a problem to the operator if the temperature is high during cutting. Now temperature rise in the tools is maximum for tough materials with low specific heat. So when you talk about the cutting tool material, okay, if the cutting tool is tough and if it has a low specific heat, then the temperature rise is high. So tough material means it can absorb energy without deforming, and specific heat. Okay, to increase the temperature of that cutting tool material, you need high amount of temperature. So that means, in other words, the cutting tool is not thermally conductive, okay, indirectly. So in such case, temperature rise will be very high. Now here we can see different zones. There are 3 during cutting process. So one is primary deformation zone, this one here, this black portion. So what is this? Elastoplastic deformation. Okay. So material will be plastically deformed, initially elastic deformation, then plastic deformation. Okay. And some kind of elastic energy will also be stored in the chip. So this is primary deformation zone. Now secondary deformation zone is here. So here in the secondary deformation zone, it is mainly plastic deformation. So in the primary, it is plastic plus elastic, both elastic deformation is there, plastic deformation is there. So it is being bent. Yes, so elastically it will be deformed, it can come back also. So ultimately, along the shear plane, it is plastic deformation. Here, the secondary deformation, it is plastic deformation only. It is due to friction. So that is sticking and sliding motion of the chip over the rake surface. So heat will be generated due to friction. Now this one here is, so this is very tiny zone here. So this is a tertiary deformation zone. Here elastic deformation will be present, elastic. So workpiece will be deformed slightly, but it will come back to its original state once the tool passes that region. So that is elastic deformation. So this is okay. There will be friction between the cutting tool and the workpiece here. So due to that, heat is generated. Now what is happening during cutting is conversion of energy into heat. So whatever energy you are supplying, most of it is converted to heat. And the temperature or the heat generated, that will influence the tool wear. If the temperature is high, tool will deform, plastically deform, so it will lose its shape. Okay, and wear will also be rapid. Tool wear will also increase. Okay, at elevated temperature, built up edge formation will also be more. Okay, and the cutting tool material will wear fast, and it affects the quality of the product finally. Okay. Once the heat is more, the surface finish also becomes poor, okay, due to built-up age. And the scaling will also come into picture now. Okay, if the heat is high, oxidation will also take place on the surface of the machined region. So that is also not good. So here we can see all these three zones here. So about 80 to 90% of the heat is generated in primary zone only. So total 98% of the energy have supplied is converted to heat. Out of that converted heat, 80 to 90% of the heat is in this region only. Okay, heat is generated, and about 10 to 20% is generated in the secondary deformation zone, about 2 to 3% in the tertiary deformation zone. Now, out of this heat, okay, 80 to 90% is generated here. So, out of that, majority amount of the heat will go into the chip. Okay, and slightly less amount of heat will go into the workpiece. Now, if you take the second zone, again, majority amount of the heat generated in the secondary zone is going into the chip. Some minor portion is going into the tool. In the tertiary zone, again, majority portion is going into the workpiece and very small quantity is going into the tool. Okay. Now, why majority portion is going with the chip and not into the workpiece means, so once the heat is generated, right, the chip is moving, okay, away from the machining zone very quickly. Okay, and heat is getting generated here and here. Now the tool is continuously moving forward, so the tool will move to the next okay material that is available in front of it. So whatever heat is generated, that will be in the uncut chip here in this region, and once the tool advances, it will be a part of cut chip. Okay, so there will not be much time for the heat to be dissipated into the workpiece. Okay, so along the chip it is going away. Same is the case here. There is not much time for heat to get into this tool region, and of course tool material is generally okay heat resistant material, okay, temperature resistant compared to chip. Chip material is workpiece material only. So workpiece material will have more thermal conductivity, so it will absorb more energy, more heat energy. Tool is thermally resistant, so less energy will go to the tool. Now, same is the case in this region also, tool and workpiece again. So naturally tool is heat resistant. Okay, so very less amount is going into the tool and majority is going into the workpiece. And this is what we want also in reality, because chip is a waste portion. Okay, this is removed and it will be thrown out. Okay, so it is a scrap. So if chip is getting heated up, its properties are changing, so that's fine. Okay, there is no problem for us. But if the heat is going into the workpiece, majority heat, and if the properties of the workpiece are changing, okay, due to temperature, then there is a problem. Okay, we don't want properties of the workpiece to be altered. Okay, so if it is going into the chip, there is no issue. So that is an advantage. And after chip, the second thing is okay, it is better that the heat goes to the tool than the workpiece. Ultimately, we want to protect the workpiece. Okay. Fortunately, again, okay, here, even though majority is coming to the workpiece, but how much this portion itself is about 2% only. Okay. Uh, so its quantity is less only, whatever heat is coming to the work. So ultimately, chip is absorbing the high amount of heat, followed by tool here. Okay. Then workpiece. So that is what we want, because workpiece properties should not change. So large part of the heat is going away with the chip. Now temperature is proportional to the friction on the chip interface. Amount of temperature that is generated here is based on the friction, okay, that is present between the tool and chip. If you see the apportionment or the percentage of heat that is going into all these three, that is first is chip. So majority amount is going into the chip. Okay, maximum portion is going into the chip, and it is followed by tool and our workpiece. So as the velocity is increasing, okay, cutting temperature is gradually increasing. Okay. So then the amount that is going into the tool is reducing. Okay, maximum amount is going to the chip only as the velocity is increasing, because the velocity is increasing means chip will be removed very quickly. So heat cannot go from chip to the workpiece or tool. So majority amount will be with the chip. Then amount of heat going to the tool will reduce with the velocity. This is expected. And blank, it will gradually reduce. So majority is going with the chip. Now effect of these cutting temperatures on cutting tool. So if the temperature is increasing, what will happen to cutting tool? Rapid tool wear, which reduces tool life. So tool wear will be very rapid. There are reasons for this. Diffusion activity increases when the temperature is increased, and tool will also lose its cutting edge shape, okay, or it will deform at the elevated temperatures. So all these will lead to the reduction of the tool life. Plastic deformation of the cutting edges if the tool is not enough hard. If its hardness is less, it may deform also. Thermal flaking and fracturing of cutting edges due to thermal shocks. So if the temperature is too high, then the tool is cooled naturally. Once the cutting process is over, or once you stop the cutting process, tool will be cooling. So during that period, the contraction of the cutting tool material will take place. At that time, there can be some cracking. Built-up wedge formation will also be high if the temperature generation is high. So those are the effects of temperature generation on cutting tool. Now on the job, dimensional inaccuracies of job due to thermal distortion, expansion, contraction during and after mission. So mainly, you will not get the desired dimensions because of the thermal distortion or the deformation. And even after cutting also, so some temperature is generated, you have cut the material. Now after cutting, so material will go for contraction. So then the dimensions will change. Okay. So ideally, there should not be any change in the dimensions once the process is over. So, but if the temperature is high, there will be some change in dimensions. Now, surface damage by oxidation, rapid corrosion, burning, etc. The machined surface will also be damaged due to oxidation. Oxidation tendency will be high once the temperature is high, and corrosion will also increase with the temperature. Okay, so the surrounding air and the chemicals, whatever present in the environment, they will react with the surface of the machined area, and they may be corroded. And burning of the surface will also take place. The upper surface, okay, will be burned and it will become very brittle, and it will, okay, there will be chipping of this okay, scale that is present on the machine surface. Now, induction of thermal residual stresses, micro cracks on machined surface and subsurface region. So thermal cracking, okay, due to variation in temperatures will take place. So that will lead to thermal residual stresses and thermal crack. So if there is any crack on the machine surface, then later on it may propagate and it will reduce the functional life of the component. Now, the analytical method to find out the average shear zone temperature. So these are the assumptions. Assumptions are, yeah, you can say assumptions. Q is the rate of heat generation during machining process. That is equal to the power consumption, because we are assuming that the energy that is spent during cutting process is almost all the energy is converted to temperature or the heat. Now QC is the rate of heat generation at the contact between chip and tool. Chip tool interface, that is QC. Now QS, rate of heat generation in the primary deformation zone. So primary deformation zone, heat generation rate is QS. Chip tool interface, that is QC. So Q is the rate total heat that is generated during machining process. So now we can write Q is equal to QS plus QC. So Q is the total rate of heat generated during machining process. QS is the rate of heat generation in the shear zone. QC is the rate of heat generation at chip tool contact. And there is one more, chip and workpiece contact, but its quantity is very, very less, so it is neglected. Now we can rewrite this equation as QS is equal to Q minus QC. Okay. Now Q is equal to cutting force into cutting velocity divided by J. So this J is nothing but a mechanical equivalent of the heat energy. Okay, Joule. And QC is equal to F into VC divided by J. Okay, QC is a temperature generated at the chip and tool interface. Okay, so this is friction force, cutting chip velocity divided by J. Mechanical equivalent of heat of the chip. Okay, and workpiece. So you can write This is from merchant circle diagram. F is friction force is equal to cutting force into sine beta divided by cos beta minus gamma. This is from merchant circle. Similarly, we know the relation between velocities. So chip velocity Vc is equal to V sine phi by cos phi minus gamma. So using these two, you can now rewrite Qs is equal to Fc into V divided by J. So from where we are writing this Qs? Qs is equal to Q minus Qc. So this is Q. Okay. Now Qc is equal to, so this one, F into Vc by J. So instead of F, you are writing Fc here. Okay. Vc also you have substituted with this V by V sine phi by cos phi minus gamma. So this is the equation, Qs. Now, let A is equal to fraction of shear energy that is converted into heat. So total shear energy may not be converted to heat. So A is the fraction. Okay, whatever shear energy is available, fraction of energy that is converted is A. That may be 90%, 80% like that. Now Q1 is the fraction of heat that goes to the chip from the shear zone. So from shear zone, okay, Q1 portion is going with the chip. Remaining will be going with the, it will stay with the workpiece. Okay, if those are the assumptions, so you can write Qs as this. AQ1, so fraction of shear energy that is converted to heat, and fraction that is going into the chip from the shear zone. And the remaining is as it is. So generally, so this A varies from 0.95 to 1. So almost all the shear energy is converted to heat. And this Q1 is about 0.7 to 0.9. So out of the heat generated, about 90% is going into the chip from the shear zone. So from heat transfer principles, we know that, okay, Qs, heat generated in the shear zone, heat generation rate, that is equal to mCp delta T. Okay, this is well-known equation. So we'll write M as rho WTO into V, that is the mass, Cp into delta T. Now from this equation, we'll write delta T. Okay. So earlier on the left hand side, we had a Qs. So that is rho WTO V Cp delta T. So now we kept only delta T on the left hand side. We have taken all other things in the right hand side. Now this is the change in temperature during cutting process. And we have not considered room temperature. Now if you add room temperature to this, so you will get the temperature during the cutting process. Okay, this is the equation now. Okay, analytical way of finding out the shear zone temperature. That is one thing. Now, the second one is experimental method to find out the temperature during cutting process. There are various experimental methods available. Okay, we'll look into few methods. So most frequently used technique is the tool chip thermocouple method. Now what is this? So Godwin's method, this was developed by Godwin. So using this method, okay, this can trigger, determine the speed temperature relationship to be of the form. So this method was initially developed and the relation between the speed and temperature was developed, okay, by this can trigger. So relation is this: temperature is equal to k times of cutting velocity to the power of m. This is empirical equation. Now here T is temperature, that is measured tool chip interface temperature, V is cutting speed, K is thermal diffusivity of the workpiece material. Okay, that is in the units of centimeter square per second. This is the principle of thermocouple. You may be aware of this. So if you take two thermally conductive materials or two wires, let us say, two different wires, and on one side, okay, you maintain some temperature, maybe you keep it in very cold, okay, ice cube. On the other side, you just heat this junction. So then there will be current flowing in these wires. Okay, that is this Godwin's principle. Principle of thermocouple is that. So there is a hot junction here. Okay, there is a cold junction. So whenever temperature difference is maintained, okay, current will flow. That can be measured using voltmeter. So based on the voltage that is being measured, the amount of temperature can be estimated. Understand? Temperature rise. What is the temperature rise? So that can be estimated based on the amount of voltage that is measured. So experimentally, so this is a tool, and of course, so this is workpiece, and here this is all workpiece, and you are providing insulation between the chuck and the cutting tool, not cutting tool, workpiece. Now, to that workpiece only you have attached one disc, okay, with the same material. So that disc will be rotating in a mercury cup. Okay, this is a cold junction. And you have tool here, cutting tool, which is in contact with the workpiece. And you have connected one, okay, voltmeter here between the tool and the cutting tool and this rotating disc. Disc is part of this workpiece material. Okay. So you have prepared one junction here. This is cold junction. This is hot junction here. Okay. Now you can, based on the voltmeter reading, you can measure the temperature. Understand? Now, why there is a mercury cup here instead of direct contact? Because if there is a direct contact, there will be some friction between this workpiece material and the conducting material, whatever is there. Okay, and maintaining uniform contact between the thermocouple and the workpiece will also be difficult if there is a direct contact. Understand? If you are using mercury, which is conductive, thermally conductive, and then there is no problem. You can maintain uniform contact and there is no friction also. So this is how you measure the temperature, okay, using tool work thermocouple method. Another method is inserted thermocouple technique. So here you see, this is the tool. So you have drilled a hole into the tool very close to the top surface, okay, and you have kept thermocouple inside it. It is touching, okay, this bottom surface, okay, at the end of this drilled hole, and the remaining portion is insulated. Okay, there is insulation here. Or a ceramic tube is nothing but insulation. Now, during cutting, so this portion will be heated up. Okay, this portion will be heated up, and this heat will go here, and it will be sensed, and you can measure the temperature. But you are not directly measuring the temperature at the chip tool interface, okay, but at some depth. Now you know the thermal properties of this cutting tool, and if you know the temperature at this location, now what will be the temperature at this location? Okay, so based on the heat transfer principles, you can estimate the temperature at the surface now. Okay, if you know the temperature at some depth. Understand? So based on that, you can measure the cutting temperature here, chip tool interface temperature. Now another method is embedded, this embedded thermocouple method. Okay, this is okay, this is fine. There is another method. Okay, if it is a turning tool, this is how you will do. Let us say if it is a milling cutter, milling process, then how to put the cutting tool into the milling cutter? It is difficult. Now here in this case, we will put the thermocouple inside the workpiece here. This is workpiece. This is tool. Okay, rotating tool. You will have these okay, cutting tool blades will be there. That is okay. Now here what you will do is, you will put the thermocouple at some depth, and you will take one pass. Okay, one cutting pass will be taken. Now you know the height and you know the measured temperature. Next time another pass. So again height will vary, temperature will vary. Like that, you come very close to the thermocouple and note those temperatures. So it will be like this. Okay, at a different depths, you will get different temperatures. And these peak temperatures will vary as shown in the second figure. Okay. So initially when the height is more, that means this HI is high, you will have less peak temperature. Then the height is decreasing, peak temperature will increase. Now here also you can see, so with the variation in height, so as the height is coming down, the temperature is gradually increasing. You see, you have to see from this side like this. Okay, height is decreasing. So then temperature increasing. Okay, it is obvious because we are coming close to the thermocouple. So like that, for different heights, we will plot a graph and you can extend that graph to meet this H0. So H0 means at the tip directly, what will be the temperature. Okay, that is theta m, measured temperature or maximum temperature. But it is difficult to extend such kind of curve. Okay, we don't know exactly where it will meet this. So for that, you take the logarithm graph. So log hi, log theta m. So it will be a straight line then. So once you get straight line, you can simply extend it to know the temperature at the surface. So this is how embedded thermocouple method works. Now next one is radiation method. So this is according to Planck's law. So power radiated per unit area per unit wavelength, okay, W lambda depends on the absolute temperature T and wavelength lambda. This is Planck's principle only. So based on that, W lambda is equal to 2 pi hc square by lambda power 5 into this. Okay, this is the equation. Now W lambda is power radiated, lambda wavelength of the radiation, H Planck constant, C, K, etc. So you have to find T. Okay. So this is one method. You know all other things except T. Using this, you find out the. But you have to measure this radiated power. Okay, there will be sensors. So you'll keep the sensor very near to the cutting zone. So there is temperature generated. So some radiation will come. Based on the amount of radiation, W lambda will be determined. And lambda will also be determined. So remaining values, you know, based on that, you estimate the temperature. One more method is micro hardness method. After the cutting, you take the cutting tool and measure its hardness. Okay. So based on the hardness, you can talk about the amount of temperature that is generated, or the based on the depth of indentation. Okay, if the indentation depth is high, what does it mean? So more temperature is generated. That's why you can get more indentation. Understand? So in that way, you will generate a relation between temperature and hardness. Understand? So if this is the hardness number I am getting, this is the amount of temperature generated. So in that way you can do. So here the disadvantage is there is a time loss between the hardness measurement and the completion of machining. Okay, during that time, so the cutting tool will be cooled to some extent, so you will not get accurate results. So here we can see some relation here. HCS, high carbon steel material. So with the rise in temperature, the hardness value is coming down. Okay. Suppose, you have done HCS material. Okay, you have done the cutting process. So you have measured the temperature. You have measured the hardness, let us say, hardness. So hardness is, let us say, about maybe this is some 700. Hardness number is some 700. So if the 700 is here, so you draw a vertical line and see what is the corresponding temperature. So we should have this ready-made Okay, data available with us. For high carbon steel, with temperature, how hardness varies. That graph is with us. Okay, based on that, okay, once you measure the hardness, so you will take that hardness and you draw a vertical line. Let us say hardness is here. You draw a vertical line and see what is the temperature. Similarly, for HSS also. Okay, so for let us say for HSS, this is the hardness that is measured after experiment, immediately after the experiment. So what is the corresponding temperature from the standard graph for HSS with the temperature, how hardness varies, that graph we have. Okay, so based on that you can estimate the cutting temperature. Yeah, I think we should stop here. Then we'll see the dimensional analysis and the remaining aspects of thermal, okay, aspects of machining, maybe 1 or 2 problems in the next class. Yeah, any doubt in today's class? I don't know, we have not interacted also during class today. Is it clear? Any doubt in today's class?
Clear, sir.
Okay, so your exam, minor exam is from 6:30. Okay, 6:30 to 7:15 in LMS. So I hope all of you are prepared well. So there will be 30 questions. So amount of time is 45 minutes. That's it. Okay. I'm just noting down the attendance. I hope that you are following the classes. Okay, of course, today's class is mainly theoretical for the last 2-3 classes. If you have any issues, you please bring them to my notice. Okay, that's all for today. Have a good day. Prepare well and write your minor one. Okay, thank you.
Thank you, sir.